Welcome to the deep dive. Ever found yourself staring at a code base thinking, how? How did we even get here?
Mm-hmm.
Or maybe you've sketched out some boxes and lines, hoping it makes sense.
Yeah, the classic whiteboard session.
Right, only to realize later the code's doing something totally different.
Software architecture, yeah.
Yeah.
It feels important, but sometimes, especially for us developers, it's kind of wrapped in this layer of mystery.
Or it just seems like something those other people do, the architects in the ivory tower.
Exactly. And often the way architecture has been traditionally presented feels, well, disconnected from the reality of writing and shipping software, doesn't it?
Absolutely. And that's why our source material for this deep dive, Simon Kuhn's book, Software Architecture for Developers, is so refreshing. It really cuts through that, offering a perspective that's much more grounded in, the developer's world.
That's exactly what we're here for. Our mission is to dive into this source, unpack its core concepts, grab the most valuable, practical advice, those real nuggets, and especially dig into this idea of doing just enough architecture. Yeah, finding that sweet spot.
We want to give you a shortcut to feeling, properly informed on this topic, moving past some of the traditional baggage.
So let's jump in and explore what that actually means together.
Okay, so right off the bat, let's tackle that core question. What is software architecture? From this developer-focused view, how does the source define it?
Well, it defines it quite simply, really. It's the combination of application and system architecture. But the key thing is, it's all about the significant elements of a software system.
Okay.
This isn't just about, fancy diagrams. It's about everything from how your code is structured right through to how it actually gets deployed and run successfully out there in the real world.
Significant elements. That sounds important. But what makes something significant? I mean, isn't every line of code kind of important?
That's a really good question. The source brings in a helpful idea here from Grady Booch. It says significant design decisions are the ones that fundamentally shape a system.
Shape it. How so?
Well, their significance is measured by the cost of change.
Ah, the pain metric. Like, how much is it going to hurt if we have to change this later?
Exactly that. These are the things you can't just refactor in an afternoon without, causing ripples, maybe breaking things, or just taking a serious chunk of time and effort.
Okay, so give me some examples. What kind of things are we talking about?
Think about the really foundational choices. The overall shape of your system. Is it a simple web app or maybe a complex microservices landscape, client server?
Right. Big picture stuff.
And the internal structure, too. Are you thinking in terms of layers or maybe components that bundle related functionality together?
And technology choices must be huge here, right? Picking a language, a framework, a database.
Yeah.
Changing those later is definitely not an afternoon's work.
Oh, absolutely. They are prime examples. And also decisions around the architectural patterns you choose to handle. Things like performance or maybe scalability. These decisions, the ones with that high cost of change, that's what architecture is really concerned with.
And if nobody is actively thinking about these significant things, what happens then? The default path.
Well, you risk ending up with the infamous big ball of mud.
Ugh.
Systems that are slow, insecure, fragile, unstable, a total nightmare to deploy, maintain, extend.
We've all been there, I think. Inherited something like that.
Probably. And it's often the result of those significant decisions just not being made intentionally or maybe not collaboratively. They just sort of happened.
So if these significant decisions are so critical, who is supposed to be making them? Is it just the person with architect in their job title?
The source really pushes back on that idea. It frames technical leadership more as a role, not necessarily a specific rank or a single person. It's about guiding those decisions, making sure the system stays coherent.
Okay, a role. So what are the key responsibilities of someone filling this role? Beyond, drawing boxes and lines.
Well, a huge part is understanding the architectural drivers. These are essentially the forces shaping the system.
Drivers? Like what?
Things like the functional requirements, what the system actually does. Then the quality attributes, how well it does it, the velocities, performance, security, that stuff.
Okay.
Also, the constraints, the real-world limitations like budget, time, technology stacks, and finally, the principles, the sort of guiding rules the team agrees on. You have to know what you're building and why to make good decisions.
And you can't just sit in ivory tower doing this, can you? The source sounds pretty blunt about collaboration.
Oh, yeah. It literally says, if you don't collaborate, expect to fail. Couldn't be clearer, really.
Wow.
You need to work not just with your immediate development team, but also with security folks, operations, support, DBAs. anyone who touches the system or is affected by it. Yeah, architecture involves a lot of negotiation and understanding perspectives outside your immediate team.
Okay, but the question that always comes up, should people in this architecture role actually code?
The source's take is pretty clear. Ideally, yes.
Why ideal?
Because you need to intimately understand the trade-offs of your decisions.
Hmm.
If you're not coding, you might propose something that looks great on, say, a PowerPoint slide.
Ah, the PowerPoint architect.
Exactly. But it might actually be a nightmare to implement or maintain in reality. Staying connected to the code, maybe through doing code reviews, is vital to avoid becoming that kind of detached architect.
That resonates. It's hard to lead technical decisions if you're not living in the technical trenches, at least some of the time.
Totally. And part of this role is also coaching and mentoring, right? Helping others on the team grow their understanding of architecture and technical leadership in general.
You know, one thing that surprised me a bit in the source was the emphasis on soft skills. Sometimes it feels like technical skill is everything in our world.
And the source really highlights that soft skills can sometimes be even more important. Things like staying positive, motivating the team, facilitating discussions, especially when there's conflict, which happens,
Sure.
and delegating effectively. There's a quote it uses, something like, a happy team is a team that delivers, and those soft skills are absolutely fundamental to achieving that.
It also uses that fascinating master builder analogy. Can you unpack that a little?
Yeah, it's pretty neat. It traces the word architect back to chief builder.
Mm.
Historically, master masons were these deeply skilled craftspeople who also designed and managed the projects.
Okay.
But over time, the design and the building roles sort of diverged. This historical split mirrors the debate we have in software today. Should the architect be hands-on or purely a designer? That analogy gives a great perspective on why we even argue about whether architects should code.
That's a cool historical link. And finally, you mentioned understanding the drivers. Does that include understanding the business itself? The domain?
Crucially, yes. Domain knowledge is essential. You really can't build a successful product if you don't understand the business problem you're trying to solve.
Right.
The source notes this can be a challenge, especially for consultants who jump between different domains frequently. It highlights the skill required to get up to speed quickly on a new business area.
Okay, so let's dig a little deeper into those architectural drivers you mentioned. These are the fundamental forces shaping things, right?
Yeah, think of them as the wind and waves acting on your system design. The source identifies 4 main types. First, and probably most familiar to developers, are the functional requirements.
Right, what the system actually does. The features, the use cases, the user stories we work on every day.
Exactly. Pretty straightforward.
Yeah.
But then you have the quality attributes, often called non-functional requirements, or maybe the assimilabilities.
Ah, yes, the infamous assimilabilities. Performance, scalability, security. Everyone talks about them, but sometimes they feel a bit fuzzy. What are some key examples from the source?
Well, you hit the big ones. Performance like response time, latency. Scalability, can it handle more users, more requests, more data? Availability, how much uptime do you actually need? That's where you hear about the 9s, like 99.9% uptime.
Which allows for very little downtime per day, right?
Exactly, maybe just a minute or so. Then there's security authentication, authorization, confidentiality, audit trails. Maintainability, testability, deployability, understandability, flexibility, robustness.
Wow, quite a list.
And even things like internationalization, I-18N, and localization, L10N, reliability, failover, disaster recovery. Yeah, it goes on.
And the source makes a really important point about defining these, doesn't it? They need to be specific, measurable.
Absolutely critical. Saying the system must be fast is basically useless from an architectural perspective.
Right? What does fast even mean?
Exactly. You need to say something like 95% of user login requests must be processed within 500 milliseconds under normal load conditions. Or the system must support 1,000 concurrent users performing core transactions with average response times under 2 seconds. Precise, measurable goals for quality. Otherwise, how do you know if you've achieved it?
Makes sense. Okay, next driver. Constraints. These feel like the immovable objects, the things you just have to live with.
Pretty much. These are the real-world limitations that are typically imposed on you, not things you choose, like time and budget, obviously.
The classics.
Also, the skills available on your team, maybe specific technologies your organization has approved or explicitly disapproved, the required deployment platform, existing legacy systems you must integrate with.
Oh, yeah, like that banking example in the source with the specific, maybe awkward XML schema you just had to use.
Exactly that kind of thing. Or maybe your organization is very risk-averse and won't touch open-source tech. or the project itself is just a quick tactical fix versus a long-term strategic investment.
Team size too, right. A small team might struggle with the overhead of some complex new technology.
Definitely. All these are limitations, yes.
Mm-hmm.
But sometimes they can actually simplify things by narrowing down the design options you have to consider. Fewer choices can be freeing, in a way.
Okay, and the final driver, principles.
These are like the guiding lights, the rules you adopt as a team for consistency. For example, deciding on a specific layering strategy like UI talks to business layer, business talks to data access, no skipping layers.
Or maybe standardizing on how you handle database access, like we always use stored procedures for these types of operations, or we use this particular ORM in this way.
Right, or how you manage user sessions. The point is consistency. They help ensure the team builds the system in a coherent way, following agreed-upon approaches.
But you have to listen to the team on those, yeah. If a principle is actually causing more problems than it solves, it needs rethinking.
Precisely. Principles should help, not hinder. They need to be living guidelines, not rigid dogma. So yeah, functional requirements, quality attributes, constraints, and principles, understanding all of these is crucial. It narrows down the possibilities and gives you a solid starting point for making those critical, significant decisions. Ignore them, and you're basically building blind, hoping for the best.
Okay, let's talk about technology. There's this maybe older idea floating around that architecture is purely conceptual, purely abstract.
Right.
And technology is just an implementation detail you kind of sprinkle in later. The source really pushes back hard on that notion.
It argues really strongly that technology choices are absolutely not just details. They are architectural concerns. They should appear on diagrams, and they need to be considered early on.
Why is that? Why can't we just, decide on Java versus .NET or Postgres versus Mongo later in the project?
Because your technology choices profoundly impact your quality attributes. How fast can your system be? How scalable? How secure? The underlying tech makes a huge difference.
Sure.
They're often dictated by your constraints, too. What platforms can you actually deploy to? What skills does your team already have? Using a technology no one knows adds risk and training overhead.
Right. And consistency, too, I guess, if everyone's using different ways to talk to the database. Chaos.
Exactly. Technology choices are essential for consistency. And there's an interesting point the source makes about deferral versus decoupling related to this.
Ah, yes, explain that one.
Well, you might think that by putting, say, an object relational mapper, ORM, between your application code and the database, you've successfully deferred the database decision. You can swap databases later, right?
Well, that's the promise, yeah.
But the source argues you haven't really deferred the significant decision. You've just shifted it. Now, the choice of the ORM itself and how you configure and use it becomes a significant architectural decision.
Because changing that ORM later is probably just as hard, if not harder.
Precisely. And crucially, adding that abstraction layer, the ORM in this case adds complexity. It's not free. You have to learn it, manage it, maybe deal with its performance quirks. Decoupling isn't magic.
Like that Silverlight example in the book. Someone thinks, let's build a rich client. Silverlight makes it easy.
Right. But then you realize building that rich client means you now need things like data services to feed it. You have new security concerns between client and server. Testing becomes more complex. Deployment is different.
Yeah, all these architectural implications that weren't obvious from just saying rich client.
Exactly. Thinking about the concrete technology choices early forces you to ask those practical, real-world questions. How do these pieces actually communicate? How do they start up? What are their real dependencies? It brings the necessary trade-offs out into the open where you have to deal with them. Nothing is free.
So all this thinking and deciding is great, but it's pretty useless if you can't communicate it effectively to the team and stakeholders. The source points out something we see everywhere in software teams, a bit of an irony.
Yeah, it's interesting. We're often really good at visualizing our process or workflow, aren't we? Think Kanban boards, Scrum task walls. We're visual there.
Right, we track the work visually.
But we often fail completely or do a really poor job at visualizing the software system itself effectively.
And the common approach when we try, just drawing some informal boxes and lines on a whiteboard or in a quick sketch.
Which, as the source points out, is often a recipe for miscommunication. Shapes mean different things to different people. The lines are ambiguous. Does this arrow mean data flow?
Yeah.
Or a call? Or just dependency? Boxes get generic labels like business logic or service layer.
Yeah, service layer tells me nothing about what service.
Exactly. Technology choices are often missing entirely. You might mix different levels of abstraction on the same diagram, showing high-level components next to specific classes, Or you try to cram way too much detail onto one picture. It just becomes confusing noise.
Total chaos. So how do we fix that? The source introduces the C4 model as a potential solution.
Yeah, C4 is presented as a really practical, lightweight approach. It's not a rigid standard, more like a simple way to think about visualizing software architecture using a series of diagrams, but specifically at different consistent levels of abstraction.
Okay. And C4 stands for?
Context, containers, components, and optionally classes. 4 Cs.
Context. That's the highest level, right? Like the 30,000-foot view, the big picture.
Exactly. The context diagram shows the software system you're focusing on right in the middle. Then it shows the key users, or actors, who interact with it, and the other major software systems it directly depends on or interacts with. It literally sets the context.
And who's the audience for that?
Pretty much anyone. Technical people, business people, managers. It's simple enough for everyone to understand where the system fits in the world.
Okay, then you zoom into the next level, container.
Right. A container in C4 isn't just a Docker container, though it could be. It's a broader term for any major, separately runnable or deployable unit or a significant data store. Think web applications, mobile apps, single-page apps, back-end APIs, microservices, command line tools, databases, file systems.
So the major building blocks.
The major building blocks, yeah. The container diagram shows these blocks. Importantly, it shows the main technology choice for each one, like Java Spring Boot web app, PostgreSQL database. It lists their key responsibilities and, crucially, how they communicate with each other, like HTTPS JSON API call or reads writes using JDBC.
And the audience here, more technical.
Generally, yes. Developers, architects, ops folks, people who need to understand the high-level technical structure and interactions.
Okay, and then you zoom in even further.
You get to the component diagram. Here, you pick a single container from the previous diagram, say, your main back-end API application, and you break it down into its major logical components inside that container.
So components aren't separate processes here?
No, typically not at this level. They're logical groupings of related code within a single container. Think of them as representing key functional areas or business capabilities within that container, like an order management component or a user profile component. They're a level of abstraction above individual classes.
And the diagram shows?
It shows these components, their core responsibilities, and how they interact within that container, which methods they call on each other, for instance. This is usually most relevant for the development team working inside that specific container.
And the final C, classes, is optional.
Yeah, the source suggests you only drop down to class diagrams if you really need to illustrate a particularly complex part of a component, maybe a specific design pattern implementation or a few key classes and their relationships. It's not meant for showing all the classes.
It sounds like that structure follows Ben Schneiderman's famous mantra for visual information seeking.
Exactly. Overview first, zoom and filter, then details on demand. Context gives the overview. Containers and components let you zoom and filter. Classes provide the details on demand only when necessary.
What makes these C4 diagrams effective, even if they're just simple sketches? Are there key ingredients?
The source emphasizes a few things. Crucially, include technology choices on the container diagrams. It grounds the abstract boxes in reality and forces important discussions. Add responsibilities to each box, a short phrase or bullet list explaining what it actually does. Don't just label it service.
Okay.
Pay attention to simple things like orientation. How are layers typically stacked in your organization's diagrams? Top to bottom, left to right. Consistency helps. And establish simple, clear conventions for your lines and arrows. What does an arrow mean? Is it dependency? A data flow? A synchronous call? Make it explicit with a key or legend. Even simple new AML diagrams benefit hugely from basic consistency.
And the source mentions other useful diagrams, too, beyond the core C4 level.
Yeah, things like a deployment diagram showing how your C4 containers map onto your actual infrastructure servers, virtual machines, PNS environments, whatever. Or maybe runtime diagrams, like sequence diagrams, but showing interactions between containers or components, not just classes, to illustrate a specific workflow.
So it's not about blindly drawing all possible diagrams.
Definitely not. The advice is clear. Draw the minimum necessary to communicate the architecture effectively to the intended audience. Start simple, maybe just context and containers. Add components if needed for specific areas. Add others if they answer important questions. If a diagram isn't adding value or isn't being used, get rid of it. Keep it lean.
Speaking of communication and diagrams versus reality, There's often this painful gap, isn't there, between the beautiful architecture diagrams, maybe pinned on the wall or in a wiki, and, well, the actual code living in the repository, the mind the gap problem.
Oh, absolutely. It's a classic situation. You look at the diagrams, and they show these neat components, maybe clear layers with strict boundaries.
The ideal world.
Exactly. But then you open the code base, and it's often just packages full of classes, maybe organized by technical type, maybe not. And it doesn't seem to clearly map to anything you saw on that diagram. As the source puts it, sometimes the architecture diagrams on the wall say one thing, but the code says another.
Why is that? Why doesn't the code just be the architecture? Isn't code the ultimate source of truth?
Well, yes and no. Code tells you what is implemented, often in great detail, but it doesn't easily or explicitly show the intent behind the design decisions.
What kind of intent?
Things like the cross-cutting concerns, how is logging handled, security, configuration. These often weave through many parts of the code, but aren't obvious structural elements. Or the overall architectural patterns being used, like maybe CQRS or event sourcing the code implements it, but the pattern itself isn't immediately visible just by browsing files.
Right, and how the system is supposed to scale, or how it integrates with external systems.
Exactly. You might be able to figure some of this out by reading enough code, but you might not even know what questions to ask. And crucially, code doesn't easily tell you how to add a new feature in a way that's consistent with the intended architecture.
So the source compares different ways to organize code to try and bridge this gap a bit.
It does. The most common default, often what you get from project templates or basic tutorials, is what it calls package by layer.
Okay, I know this one. You have folders or packages like com.example.web, com.example.ui, com.example.service, com.example.domain, com.example.data.
Right. It's easy to get started with, and you can kind of see the overall layering structure. But the downside is that adding a single feature often means jumping between many different layer packages, which would be cumbersome.
Yeah, touching files all over the place.
And worse, if you're not really strict with visibility modifiers, like making classes internal or package private where appropriate, it can easily devolve into a big ball of mud, where code in any layer starts calling code in almost any other layer, bypassing the intended structure. And it doesn't really scream the business domain at you. It screams technical layers.
So what's the alternative suggested?
Package by component.
Yeah.
The idea here is to organize your top-level code structure around coarse-grained architectural components, often reflecting key business capabilities or domain concepts.
So instead of web service data, you might have packages like com.example.orders, com.example.customers, com.example.inventory.
Exactly. And inside the com.example.orders package, you'd then have the web controllers, service classes, data access objects, and domain entities related only to order management.
So the layers become a secondary organization within the component package.
Precisely. The huge advantage is that this makes the intended architectural components explicit in the code structure itself. It's much easier to see the main building blocks of your application. And you could potentially use language features like access modifiers in Java or C# to enforce boundaries between these components more effectively, maybe making most classes inside a component package private or internal by default.
That makes the code base feel much more like a direct representation of that component diagram we talked about earlier.
That's the goal. It closes the gap. And the source also briefly mentions you can use metadata, like annotations in Java or attributes in .NET, to explicitly tag classes or modules with architectural information, although package by component is perhaps the more fundamental structural approach.
What about this idea of architecture as code? Can we just automatically generate diagrams from the code? Wouldn't that solve the problem?
Well, the source is a bit cautious here. It notes that while tools exist that try to do this, analyzing code dependencies and generating diagrams, it's actually really hard to automatically generate meaningful, high-level architecture diagrams directly from code alone.
Why is that?
Because code tells you what is implemented, but it lacks so much necessary context.
Yeah.
It doesn't know about the users, the external systems it integrates with, the underlying infrastructure, the deployment strategy, or crucially, the intent and the rationale behind the structure. Auto-generated diagrams often end up being overly detailed, messy, and missing the big picture.
So you might need to add extra information.
Yeah, you often need to enrich the code with specific metadata or use separate definition languages like Structurized or DSL, which Simon Brown also created, where you explicitly define the architectural elements and relationships. That helps bridge the gap and allows tools to generate more useful higher-level views that align with models like C4.
Okay, another really common pain point, especially in teams trying hard to be agile, documentation. The Agile Manifesto famously includes the phrase, working software over comprehensive documentation.
Yes, and as the source points out, that phrase is perhaps one of the most misinterpreted parts of the manifesto.
Mm.
It's often taken to mean no documentation needed, or even documentation is bad.
Right, just read the code.
Exactly. And while the code is the primary source of truth about what the system does right now, the source argues strongly that it doesn't tell the whole story. For anything non-trivial complex systems that live for a long time, systems where teams change frequently, like with outsourcing, some amount of supplementary documentation is absolutely necessary.
So how should we think about it then, if not a massive, static, upfront specification?
The source suggests a really nice analogy. Think of supplementary software documentation as an evolving travel guidebook for your software system.
A travel guidebook. I like that. You don't necessarily need every single street name and house number on page 1, but you definitely need maps, some context about the place, practical advice on getting around.
Exactly. It's not meant to be a static historical record written once and then ignored. It's a living guide that helps people understand, navigate, use, operate, and change the system effectively. What kind of sections does a good guidebook need?
Okay, walk me through the suggested sections for this software guidebook.
It starts with context, just like the C4 diagram, explaining what the system is, its purpose, who uses it, how it fits into the wider technical and business environment. Maybe embed that C4 context diagram right there.
Makes sense. Get oriented first. Then what?
Then you need details on those key architectural drivers we discussed earlier, the precise measurable quality attributes, the constraints that shape the design, the principles the team follows for consistency.
Laying out the foundational forces.
Right. Then the core maps, the software architecture section. This is where you'd put your C4 container and maybe relevant component diagrams, explaining the key building blocks and their relationships.
Okay, the structural overview. What else?
Practical stuff. Documentation for external interfaces. How do we talk to that other system? Maybe a code section, not duplicating code comments, but explaining significant or complex implementation details, patterns used, or areas that are hard to understand just from reading the code.
Got it.
A data section. What's the conceptual data model? How and where is data stored? Who owns it? Then infrastructure architecture. What's the physical or virtual hardware environment it runs on?
Getting into deployment and operations.
Exactly. A deployment section, how do you actually map the software containers to the infrastructure? What's the deployment process? Rollback strategy. And an operation and support section. How do you run it, monitor it, manage it? Where are log files? What configuration is needed? Any essential housekeeping tasks?
And one more crucial piece you mentioned earlier, a decision log.
Absolutely essential, yes. This is where you record the significant architectural decisions made and, critically, the rationale behind them. What alternatives were considered? What were the trade-offs? Why did we choose this technology or this pattern? What was the context at the time? Capturing the why is key to understanding the system's evolution and avoiding revisiting old arguments.
That guidebook analogy really holds up. Different maps for different levels of Zoom, like C4, the history and culture, the decision log, the principles, practical info for getting around, deployment, ops.
Precisely. And it helps distinguish this kind of product documentation about the software system itself from project documentation, which is more about the development effort, meeting notes, schedules, etc. The guidebook is focused squarely on the system.
All right, let's wrap this up by tackling that perceived conflict, maybe the elephant in the room for some teams. Agile versus architecture. It feels like a constant debate sometimes.
It really does. And the source argues quite strongly that it's largely a myth, or at least a misunderstanding. Agile projects absolutely need architecture, especially when you have complex non-functional requirements or tricky constraints you have to meet.
So it's not whether you do architecture?
Exactly. The difference isn't whether, it's how and when you do it. It's about the execution of that architecture role within an agile context.
So clearly not big design up front, BDUF, where you try to spec out everything in minute detail before writing a line of code.
Definitely not BDUF. The source points out the classic problems with that. It often leads to analysis paralysis. You spend ages designing things that might change or be wrong. It delays getting feedback. And frankly, coding can become a boring, paint-by-numbers exercise implementing someone else's potentially outdated plan.
Okay, so BDUS is out. But the opposite extreme, doing no architecture thinking up front, just diving straight into code that's bad too, right?
Also a potential disaster, especially for anything non-trivial. That's often how you end up with the big ball of mud we talked about earlier. Inconsistent approaches, duplicated effort, core quality attributes missed, lack of technical direction, chaos of a different kind.
So the sweet spot, the agile-friendly approach, is somewhere in the middle. What the source calls just enough upfront design.
Precisely. It's about finding that balance. I mean, focusing your upfront thinking and design effort specifically on identifying and making the significant decisions early.
The ones with the high cost of change.
Yes. The ones that are inherently high risk, maybe because they're complex or new to the team or foundational to the system structure, the things that will be really painful and costly to change later if you get them fundamentally wrong.
But why do we need any upfront design? Why can't everything just evolve organically as we build?
Because some things, particularly those cross-cutting quality attributes like performance, scalability, security, resilience, they're incredibly hard, sometimes impossible, and almost always very expensive to just bolt on later.
Right, you can't easily sprinkle scalability onto a system not designed for it.
Exactly. You need some upfront thinking about these major vulnerabilities and constraints to ensure your basic structure and technology choices aren't fundamentally undermining them.
Yeah.
You need to avoid painting yourself into a corner on the stuff that really matters and is hard to fix.
Okay, so how do you figure out what is significant and high risk enough to warrant that upfront attention versus what can safely evolve later?
The source suggests trying to quantify risk. Maybe thinking simply in terms of probability, how likely is this to go wrong or be insufficient, and impact, how bad would it be if it did. Low, medium, high for both.
Like a simple risk matrix.
Yeah, something like that to help prioritize. And it offers a really nice collaborative technique for doing this called risk storming.
Ooh, tell me about risk storming. Sounds dynamic.
It is. The idea is a whole team gets together, perhaps using some initial architecture sketches, like C4 diagrams, as a focal point. Then, individually and silently, everyone brainstorms potential risks onto sticky notes, things they're worried about, uncertainties, potential problems related to the proposed architecture or technology choices.
Okay, individual brainstorming first.
Yeah, maybe using different colored stickies for perceived severity or impact, high, medium, low. And you stick them all up on the diagrams or a board, group similar risks together, and then discuss them as a team.
So collective understanding and discussion.
Exactly. You discuss, clarify, maybe reprioritize based on the collective wisdom. And then crucially, for the highest priority risks, the team figures out mitigation strategies. What can we do now or soon to reduce this risk?
Like what kind of strategies?
Could be anything appropriate. Maybe more research is needed. Maybe we need to build a small technical spike or prototype to test an assumption or technology. Maybe we need some specific training. Maybe we need to adjust the architecture or change a technology choice. Maybe we just need to explicitly document the decision and the remaining risk. The point is, it's a proactive, team-based way to uncover and address the scary stuff early.
So just enough architecture in an agile context really means focusing that upfront collaborative effort on understanding the core structure, communicating a shared vision using simple diagrams like C4, and actively identifying and mitigating those high-risk, significant decisions, especially the ones impacting qualities or constraints that are hard to retrofit.
That sums up perfectly. The source suggests a minimal set of architecture practices for this just-enough approach. 1. Understand the structure. Get clarity on the significant elements down to maybe containers components. 2. Create a vision. Communicate that structure using simple shared diagrams. 3. Identify and mitigate risks using techniques like risk storming and targeted experiments or spikes.
And deciding exactly where that just enough line sits. That depends, right?
Absolutely. It depends entirely on your specific context, the experience of your team, the complexity of the project, the nature of the domain, the severity of the quality attributes and constraints. It's a judgment call, but this approach gives you a framework for making it.
Wow, okay. We've covered a huge amount of ground there in this deep dive, drawing heavily from Simon Brown's book. It really does shift the perspective on software architecture, doesn't it? Away from that potentially abstract, BDUF-heavy idea.
Yeah, towards something much more practical, grounded, and developer-centric.
The key takeaway for me seems to be it's all about understanding and actively managing the significant decisions, the ones that are really costly to change later.
Exactly. And seeing the architect role not just as a title, but as a collaborative technical leadership function, one that ideally stays hands-on with the code.
And understanding those architectural drivers, the qualities, the constraints, the principles, that's absolutely fundamental because they are the forces literally shaping your system design. Plus, really internalizing that technology choices are core architectural decisions, not just implementation details you tack on at the end.
Right, and effective communication is so vital, moving beyond those messy, ambiguous whiteboard sketches towards more structured, layered views like the C4 model provides, and recognizing that while code is primary, useful, evolving documentation, that guidebook idea is often essential for capturing the context, the rationale, the why, that code alone doesn't easily show.
Ultimately, it kind of boils down to finding that pragmatic, just enough sweet spot, doesn't it? Focusing collective effort on identifying and tackling the highest risks early through collaboration, rather than getting bogged down trying to over-design everything upfront or, conversely, doing nothing and hoping for the best.
Yeah, hopefully this deep dive gives you, the listener, a clearer mental model and maybe some practical techniques or ways to think about architecture from your perspective as a developer.
So, here's a final thought to leave you with, building on all this. Think about the last software system you worked on. Could you easily explain its most significant architectural decisions and its key drivers? The main quality goals, the big constraints to a new team member joining tomorrow.
Good question.
And maybe more practically, what's just one small, tangible step you could take this week, perhaps inspired by something we've discussed, like the C4 model or the idea of a decision log, to make the architecture of your current project slightly clearer or easier to understand for your team? Even just sketching a simple context diagram or writing down the why behind one key recent decision.
Just one small thing, something to mull over.